Oh man, why has this got to be so messy? I guess I'll have to clean this up. Ooh, cannoli. Yay, we cleaned up our mess. Now it's a different kind of mess. So I have been presented with a problem that I need to try and figure out, or I'd like to try and figure out, and it's led to several questions that I have, and I thought it would be fun to explore those questions and see if we can't find an answer to them. So in today's episode, we're going to be speaking and proving more electrical theory. So I'm Alex. Welcome to the Renaissance Builder. So here's the general idea. The thing that I'm trying to figure out is I have a voltage circuit that I think is spiking and has anomalous, that's a complicated way to put it. Basically, I got some problems on an input line voltage to a VFD, or several VFDs, that I believe is leading to them prematurely failing. You saw the video of the VFD that I took apart, and you saw how the traces for the input voltage were straight up blown clean off the board. That's why I'm believing, it was off the same job, that's why I'm believing that there's some anomalies. The problem I faced with is my oscilloscope, I can't talk. My oscilloscope only reads a sweep of 200 volts. So trying to read a 480 volt circuit just doesn't really do me a whole lot of good. So what I'm looking to do is I need to drop that voltage. So I need to drop that voltage into something that I can read. There's two different ways to do that. I can either do that magnetically with a transformer, or I can do that resistively with a resistance-based voltage drop circuit. Now, these two options have very different principles involved. The transformer uses the magnetic energies created by a building and collapsing voltage to amperage to magnetic flux setup, which is how transformers work. It uses that and the transformer principle to drop the voltage. So I'm literally using one voltage to generate another lower voltage. So that works, but what I'm actually afraid of is by using a magnetically based voltage drop that it'll actually change the sine wave form that I'm looking for, and it may actually filter out the spikes that I want to catch. Whereas a voltage drop circuit works on more of a, well, there's actually a law. So Kirchhoff's law states that every voltage dropped, or the sum of every voltage drop in a circuit, will equal source voltage. What that means is for every resistance that you have in a circuit, there's a voltage drop. It uses a certain amount of voltage at that resistance. And if you add all those up, then you will get source voltage. I.e., if I have a 10 volt circuit and I have 5 resistances, each using 2 volts, then those 2 volts dropped at each resistance equal 10 volts. So that's the difference there. Now there's no magnetics involved, so I believe that using a voltage drop circuit based on resistance may give us a cleaner signal to see what's going on in the line voltage. But I could be wrong. The resistances may actually end up filtering some of the voltage spikes that I'm looking for. Either way, we're going to put both of these circuits together and see how they work out with the oscilloscope. Also, I'd like to mention, I have talked my ears off, well, I've talked your ears off, as long as you've been listening, to about all these sine waves and stuff, you know, with the whole whiteboard and all my pictures and everything. So far I've drawn a bunch of pictures, and I'm like, you know what? This is a perfect video. I have an oscilloscope, so I might as well show you exactly what I'm talking about and actually show you the sine wave coming out of 110 volts. So, in today's episode, we're going to do a little experimenting, as well as you actually get to see firsthand what we're actually talking about. First things first, let's start with a transformer. It'll be the easiest. Now I have an old junky transformer here that I don't know where I found the thing, but it's dirty, old, and it was, well, actually, I got to make sure this thing's even good yet. So we're going to break out our handy dandy multimeter and test this here transformer. Just give me resist. I'm on the wrong one. I'm a genius. All right, so yes, that's 0.9 ohms, 1 to 0.9 ohms. Now I'm going to check to see if it's shorted. Oh well, out of limits. On the secondary and the primary, yes, is 123 ohms. Uh-oh. And 46 million ohms. This meter can't even read million ohms that well. We may blow the breaker on this. We may not. Either way, we got like 47 million ohms to ground on the primary coil. That's a lot of ohms, so I think we'll be all right. But here's the problem with my transformer. This transformer is for 480 volts to 24 volts. Well, I only have 120 volts. So I got to do some math here and figure out, basically, I believe it's divided by 4. So 24 divided by 4 is going to be, well, a number. But basically, we're going to feed it 120 volts. And then we're going to get a voltage off the secondary that we can read. Well, actually, I can read the 120 volts with this thing. That's not that big of a deal. But the point is, I want to see what happens. We're going to read the input line voltage and the output voltage, secondary voltage, to see if it made a change in the sine wave. And the cool part about this oscilloscope is I'll be able to overlay the signals and see how much of a difference there is. So I'm going to go ahead and get started setting this up. Okay, now at this point I've set a bunch of stuff up and I've wired up our transformer here to a 110 volt plug. And I didn't do the math calculation yet, but what the hell, I figure we'll wing it this time, right? Because that's what we do here. All right, so let's put the meter leads right now. What I want to do first and foremost is I'm going to plug this in, and then we're going to take a reading of what we actually get as far as voltage from our output, as well as I want to see if one leg is better to bond or ground than the other, because we need this to be grounded in order for the entire trace system to work. This is a 4-channel oscilloscope, but unfortunately every channel needs to be commonly grounded in order for it to overlay properly. So I need that to be bonded so that I can use a common ground on everything. So that's what we're going to try and figure out. So I'm going to go ahead and plug this in. Well, nothing blew up, so we're good on that front. Now we're going to go ahead and take a voltage reading and see what we're getting for an output. 5.9 volts. All right, so we're getting 5.9 volts out of this thing. Now I have this transformer grounded by a screw right here to the chassis. So we're going to go ahead and see what that takes to ground. All right, so I'm going to go with the weaker of the terminals and say we're going to ground that so that we have a grounded coil. No power. Now, it's really not that complicated. All I need to do is ground that coil. Now, at this point, you might think, like, why in the world am I doing this? I'm going to short the transformer. What shorts the transformer is when you take power to ground. So as long as one side of the transformer is grounded, that's okay. But then if we take the other side to ground, then it's a dead short. So at this point we have the resistance of the air, which is significantly high, and it's not going to pass any electrons, at least not a significant amount of electrons. That provides a common grounding for our system to work. So we're going to plug it back in, and now we're going to take our voltages. Now we have 5.9 volts to ground. Now, I'm not an engineer, so I can't explain this 100%, but basically what this is going to do, in a unit that uses these transformers, when you ground one side of the transformer, not only are you stabilizing the transformer itself by grounding out some of those peak voltages that just happen with all the magnetic frequencies going on here, so you're stabilizing it, you're also providing a point of contact so that if you need to take something to ground, your chassis is grounded. At this point, now I have my meter lead for my oscilloscope, I can hit that to ground here. So now this system is grounded. Now what I'm going to do is give us power. Yes, I have a mess. So now what I'm going to do is give us power to the rest of it so we can start measuring voltages and looking at the voltages. So what I have right now is it set up so we're going to look at the 120 volts coming out of the outlet. Now, I went ahead and took a reading, and I've got 120, 119 to 120 volts RMS coming out of the outlet. Now, RMS stands for root mean square, and there's like a whole bunch of engineering terminology and stuff that goes into this, but essentially, RMS is not this meter does not read the peak to peak or the peak voltage coming out of your outlet. Pretty much every meter you're going to get off the shelf, except for an oscilloscope or a graphing multimeter, is going to give you an RMS. This happens to be a true RMS, so it's a little different because it calculates the frequency into the equation. But pretty much everything is going to give you an average. So what I'm going to show you, and I need to redo my trace, obviously, because I'm off the board. So I need to redo my trace. But what I'm going to show you is the peak voltage. And if I do my math right, we should get 169 volts peak. Yeah. Where that matters is when you start doing all these wonderful experiments in electricity, especially VFDs and rectifiers and all this, we actually have a peak voltage a lot higher than our RMS voltage. So we have more energy to work with when we go to DC from AC. Here's what I've been talking about. This is our sine wave. And 0 right here, wow, our trigger's pretty low. But 0 right here is this matter right there. So that's what I've been meaning. That's what I've been showing you. That is the sine wave. See? You can see it. What I'm looking at now, at this point, I have a reading of 166 volts. Now we said 169, right? You know, hey, real life errors, 3 volts isn't really that big of a deal. But my point is, you can see that our peak voltage coming out of the outlet is more than 120 volts. It's actually 160 plus volts, almost 170. So that's the difference between RMS and peak voltage. Now we're actually seeing this, which I think makes a difference, and it's pretty neat. Now let's take it a step further and check out our 5 volts. Now we have our setup done here. I've got the traces set up, and you can see in actuality that you can see it's actually following pretty close. Now I'm going to change this up a little bit. I can magnify one trace over the other so I can get a much more clear layout versus them. Right now I just have it laid out so you can see the difference. We have the yellow trace is line voltage 169 volts, and the green trace, which is actually reading 8.5 volts. So the green trace is reading 8.5 volts, and it really does look like they are pretty much mimicking each other, which is actually a good thing. So bear with me here a little bit. I'm going to lay this out so it's even more of an overlap, so maybe we can see it a little better. And now what I've done is I've set the trace amplitude differently between the two of them, so that one is looking at, I think it's 20 volts per sector, while the other one's looking at 400 volts per sector. But either way, it gives us an overlap and exact match. Now, I know you can see this on screen, but I'm going to bring the camera a bit closer so that you can see exactly what I'm talking about. Alright, so I'm holding the camera, so apologize for any shake, and obviously it's, you know, I'm recording off of a screen, so be that as it may, there's a bit of glare. Now you can see by this information down here, this is live. We're not reading this fake. I'm not just showing you a picture, because I know this tends to look, you know, a bit picture-y, but I'm not just showing you a picture. This is live information. And if I get down here real close, you can see I got 162 volts peak on the yellow, max is 163, and that's measured by this line right here at that peak. If I took it over there, I'd probably get a little bit higher yet. And then On the low voltage, 8.24 volts. So if you look at the sine wave between these two, they are almost identical, which is awesome. And in fact, our 120 volts, aside from this here peak right here, the fact I got a peak right there, is almost, it's very clean, actually. I'm very impressed by that. But both our signals are almost mirroring each other, which tells me that if I want to use the transformer voltage drop to get an image of what our 480 volts is doing, that could definitely work. So let me set the camera back up, and there you guys have it. That's an oscilloscope, and that's looking at a transformer versus actual line input. Now for my next trick. I'm going to do the voltage drop. Oh, dropping stuff over here. This is a mess. Don't do stuff like this, because it's a mess. So for my next trick, we are going to do the voltage drop method. Now the voltage drop method involves taking resistors. You need 2 resistors, and then you read the voltage between those 2 resistors. And the way this works is each resistance in a circuit uses a certain amount of voltage. This applies to alternating current as well as DC current. Because, as I keep saying, alternating current is just DC current that crosses 0. See that? Anyhow, so they behave the same way. Not exactly the same way because of the fact we're decreasing and increasing the voltage across 0 and going to negatives and all. There's other behaviors involved, but that's a day for a more complicated discussion. So for now, we can know that we apply resistance, it works the same. So the way this circuit works is, let's just cut it easy and say I got 10 volts applied, right? So if I have 10 volts and I have 2 resistances, say I have 2 ohms and 2 ohms, then the voltage I read between those resistances is going to be 5 volts because each resistance is using half the voltage, which means at the beginning of the first resistance I have 10 volts. At the end of the circuit I have 0 volts. In between the two I have 5 volts. It's a voltage drop. So what I need to do now is figure out, I already know that I need 10,000 ohms to drop 120, well actually I got to recalculate this because I have 160 volts and then I have a limit of 3 watts. So I need to recalculate my resistance that I need for this to get total resistance. Once I have total resistance, then I can add some resistance to get the voltage drop that I'm looking for. And what I'm looking for is I want to get close to the voltage. I want to get close to the voltage that our transformer here is producing so we can measure it against, overlay another trace, and see how that works. I have assembled my resistance drop circuit, which totals approximately 13,000 ohms. So at 13,000 ohms, I'm getting less than 3 watts, and these resistors are rated for 3 watts, so we should be good with that. Now what I'm going to do is I'm going to set up the next trace and connect it. Now you may notice already, if you take a look at the oscilloscope, that we have already introduced quite a bit of static into our secondary transformer. That is quite a lot, especially considering it's only 8 volts. There are a lot of voltage spikes going in on that. So I'm going to go ahead and set this thing back up for another trace. And with those 3 traces, now I'm going to connect up to our voltage drop and see what we get. Oh, all right, so that trace gets a lot more. Let me adjust the screen so that we can see it as a decent overlay. Trace 3, let's set it to 50, perfect. All right, that is 18.6 volts, so there we have it. Now I have 3 traces on here. I'm gonna do the camera thing again because I want to show you guys this up close and personal. I think it's pretty awesome to see this, and it's actually kind of revealing. So let me reset this up to show you guys up close what we got on screen here. All right, so you can actually see my reflection. This doesn't have a very good anti-glare reflection, but it's a little foggy, but you can see here. So we have 3 traces. Our yellow trace is 120 volts, and you can read over here. See, that's the 120, right? And this up here is 160. And if you read down here, if you get in real close, that's 163 volts. Looks like we got 163 max. So right there where the cursor is, you can see here, I've got 420 volt and 50 volt swing. So this one's 400 volts per sector. Well, actually it's 400 volt swing total. And the other one's 20 volt swing total, and the other one's 15 volt. So this is our wall power coming straight out your wall. That's what that looks like. You can see over here our 0 is this line. So we're going positive, then negative, then positive. This green line that you can see flickering now, that is a result of the feedback voltage from the resistive circuit on the same ground. Now that, if we were dealing with some really high-powered finicky stuff, could actually result in damaging the transformers or any electronic circuit in there, because those are voltage spikes. But this is just a basic transformer. We're not actually loading it, so that's the difference. And then our blue line is the resistive voltage drop. So basically what we're proving here is that, you know, minus this here spiking, if I had them on separate grounds, you wouldn't see this. But since we're overlaid, you know, they're feeding back on each other. This does prove that it compared to an inductive, sorry, that was the catch, prove to an inductive, a resistance is more stable. It's not affected by feedbacks nearly as much. But overall, I think we're looking pretty good in this. And one thing it does prove is that whether we're talking inductive or resistive voltage drop, we are mirroring pretty darn close the actual source voltage. So that's pretty neat. I honestly thought we were going to see some different feedbacks on the inductive voltage drop, but we're not. So I'm pretty cool with that. And you guys get to see an oscilloscope and see the stuff I was talking about before. So that does it for today's episode. What I wanted to test out, whether a voltage drop circuit resistance based was going to work any better than an inductive based, right? Yeah, we're putting flowers in it and everything. An inductive based voltage drop versus a resistive based voltage drop. I wanted to see which one was going to work better, and I thought we were going to see different feedback voltages on the inductive based, but I'm not seeing that. So that tells me I can use either the inductive or the resistance. So I guess we'll see how that goes. I'm kind of leaning more towards the resistance because it does appear to be a more stable voltage drop, but yeah, it might just be cheaper just to use the resistance. Well, actually it's not, because I have the resistors here, so it's cheaper to use the resistors. Yeah, so I'm going to end up using the resistors. So I'm going to build a resistor for 3-phase voltage drop. The other thing, for all you wonderful doubters out there that didn't think I had an oscilloscope when I kept talking about, oh yeah, I got one of those. Ha. And for all you guys out there that maybe are like kind of lost in space with, you know, oh, what in the world is he talking about? A sine wave? Like, what's the electricity doing here? This is what it's doing. This is what I'm talking about. Now, I can use this in future episodes to talk about digital circuits and different kinds of, well, sine waves. I mean, we've got square wave and toothed, and, you know, this is called a sinusoidal sine wave. You know, there's all kinds of different things go on with electricity. So it's interesting to see that, and I do want to start using this to actually measure things as far as those transformers and the Jacob's ladder stuff goes, but I have to do that inductively because there's just no way I can get enough resistors to do a resistive voltage drop. So, and the inductive circuits even are ungodly expensive, so I'm going to have to come up with a way to make my own inductor to read the voltages, or at least get an idea of what's going on with that circuit there. Either way, interesting stuff. I hope you guys learned something today, because this was actually really fun, and we confirmed something that I wasn't sure about, and we got to see a lot of, well, science, honestly, of what electricity actually does in, well, every day that we use things. Every day that you plug something into your 110 volt outlet, you got one of these transformers that's like doing something with that energy. And if you're talking about computers or any computer related item that you're using, I guarantee you, you have a voltage drop circuit in there somewhere. So this is stuff that we run in, that we use every day without even thinking about it. And this is how it works. So, thank you very much, guys, for watching. I really appreciate it. If you like this video, go ahead and throw a thumbs up in there for me. And by all means, please hit that subscribe button and make sure you hit the bell icon for future, crazy experiments and sciencey stuff that we get to see. Again, thank you very much for watching. You guys have a good night.
Bye-bye.